Hello. Can everyone hear me? Uh, okay. Okay, so today we're going to be going over the basics of combinatorics. Uh, so combinatorics is basically just means counting and probability. Wait, okay. Uh, and so most of what we're covering today is pretty basic stuff. So you might already know it. If that's the case, you could just like tell me to speed up if you want. Uh, okay. There's supposed to be a table of contents here, but it didn't render for some reason. Okay. Okay, so our first topic is the permutation. So, and here's the definition of a factorial. It's just the product of the first n numbers. And here's and you should like take note of this because this isn't like intuitively obvious, but like we define 0 factorial to be 1 because it's convenient and it like works with the other definitions we have. And here's how it's like useful for accounting. So a permutation of an ordered set is another ordered set with the same elements. So a permutation of 1, 2, 3, 4, 5, 6, the first 6 numbers, the first 6 positive integers is like, these are 2 examples here. And so like obvious questions, how many permutations are there like for 1, 2, 3, 4, 5, 6? Now, so we have 6 ways to choose the first number in the permutation because it can be any of 1, 2, dot 6. And then we have like 5 ways because we can't choose the number that's already been like used. So say it's like 2, we can't use 2 again, but we can use like any of the other like numbers here. And there's like 5 of them. Okay, and then we do the same process again. So like, say we choose like 3 as our second number, so we have like 2 3 so far. Now we eliminate 3, and we have 4 ways to choose the third number. And we do that. And then this turns out to be our like factorial from before. It's like 6 times 5 times 1. And that's just 6 factorial, and we can just compute it out to be 720. And here's a more general formula. And also note that this doesn't just like apply to numbers. This applies to like any like kind of object. Like if you have like some red, so say if like you have red ball here, a green ball, and a blue ball, and you want like shuffle them around, there's like 6 ways. There's like 6 possible permutations of RGB. Okay, and now we're going on to like the main topic here, the combination, or like the choose function. So this is there's the number of ways to choose k objects out of n objects where order does not matter. So for choose 2, it's like counting the number of ways to choose 2 of these 4 objects. And I'm going to enumerate them briefly here. So there's 6 of them, and this like matches up with the formula we gave. It's kind of crowded here. So, and here's like the reasoning behind the formula. So when we're picking k objects out of n, if we do like if like what we're choosing is ordered, then it's like similar to permutations. So the first object has n choices, the second object has n minus 1 choices, and so on. Then we have this like so. But if order doesn't matter, then each combination is listed k factorial times, because remember our formula from before. There's like k factorial ways to permute an ordered set of k objects. So, and all of these k factorial like ordered sets are actually the same unordered set. So we have to divide by k factorial too. And that gives us our formula here. So does anyone have any questions here? Because this is like the main formula we're going to be using for like most of the lesson. So you kind of need to understand how it's like derived. Okay. So here's some exercises. I'll wait like a couple of minutes to like allow you guys to like solve them by yourselves. Okay, so hopefully you had some time to think about it. Okay, so here's the solutions. Wait, oh, sorry. There's like another exercise. Here, I'll give you like a little more time to solve this one too. If you still need to go back to the previous exercises, just tell me. Okay, so here are the solutions to the exercises here. So the first one is indeed 100. So it's just the definition of the factorial here. You rewrite 10 factorial as a like multiple of 9 factorial and 11 factorial as a multiple of 9 factorial. So you can cancel stuff out and yeah, you get 100 in the end. And for the second one, okay, so we have like 4 colors here, but we're going to only use 3 colors. So we have to like there's 3 ways to choose what colors we're using. And this makes intuitive sense because we need to choose a single color that we leave out. And there's like 4 colors that we could leave out. Then we have like 3 factorial ways to permute the colors. And then we just multiply these two together to get 24. Okay, this one's a bit more tricky. Well, not really. It's the definition of like the choose function. So we're given that there's 2 possible ways for 2 people to be chosen from like say n people. So by definition this is like n choose 2, and this is equal to 10. And we just solve the quadratic that we get from using our formula here, and then we get n equals 5. Then we apply the choose function again to get 10 ways to select the 3-person planning committee. Also notice this is the same answer as, or well, it's the same number as this. That's not a coincidence. N choose k is equal to n choose n minus k. Because if you think about it, you're basically taking the complement of the original k objects. Okay, so how many line segments can have both their endpoints located at the vertices of a given Q? Okay, so here's a sketch. Now, so this one's also a bit more tricky than the previous exercises. So line segments uniquely determined by its 2 endpoints. Any line segment has 2 endpoints, and any 2 endpoints has a line segment. So that's true. So there's 8 vertices that we can choose from, and we need 2 endpoints. So 8 choose 2 equals 28. Okay. Now we're going on to independent and dependent events. So here's some like definitions or notation. So P of X is the probability that event X happens. P A given B is the probability that event A given event B's already happened. Given B if B already happened. So, and here's the definition of independent and dependent. So if it's independent, like intuitively, events A and B don't affect each other. So like the probability of B if A happens, and the probability of B if A happens, or like it doesn't change from before. So, and 2 events A and B are dependent if and only if like the probability of A given B is not the same as it was before. With the like, it's not the same as just the probability of A happening. Okay, and here's some like exercises. These don't really like use. You don't need to use the notation from before, but it's like kind of useful to like keep track of what you're doing. So I'm going to be giving you like a couple of minutes to solve it. Okay, so I hope you guys had enough time. If you didn't, let me know. So the first problem. So notice that like all of these guys like rows are all independent. Like obviously, uh, like the behavior of like the rows don't depend on like what happens to the other rows, and so we introduce a technique called complementary counting here. So we find the probability that this, like, do we find the complement of this probability or the probability that this doesn't happen? And then because probabilities sum to 1, we just subtract from 1 in the end, and we get our like wanted probability. So there's like 3 prime numbers from 1 to 6, 2, 3, 5. Then the probability of getting a prime number on a row is 1 over 2. Or about probability of not getting a prime number, but they're like the same anyways. So because the rows are independent, the probability of not getting a prime number on each row is 1 over 8. And then we just subtract from 1 here to get 7 over 8. Okay, and here's the second exercise. So if some days sunny, then there's a 1 over 5 probability of rain the next day. If some days rainy, there's a 1 over 20 probability of rain the next day. So, and this again introduces a new strategy here. This is casework. So the probability that there's rain in 2 days is dependent on the probability that there's rain tomorrow. So we need to do casework on if there's rain tomorrow to like actually find the probability. And then we just do these 2 cases here. And this is our answer here. So okay, now we're going to do probability by counting. So basically we're just going to be counting the number of ways for something to happen, and we like put it over the total number of ways something could happen. And this only works if each possibility has an equal probability. And yeah, okay. So, and this is most often used in coin problems because like each sequence of coin flips is equally likely to happen. And here's like a kind of common misconception. It's not as like obvious as this sometimes, like, but it's kind of, yeah. So yeah, it's not as obvious as like this, but like it actually happens quite often to even like experienced people. Like say you're trying to find the like, so say you have like some bug and it's like traveling like either up or right here on this grid, and it stops when it reaches the rightmost wall here. So like there's a kind of common like mistake a lot of people make here is that they count the number of ways. Oh, and say you want to like find probability that it reaches like this corner here. A lot of people just like finding number of ways to get to this corner and then just like divide by like the total number of possibilities. But like that's not, but the thing here is not all of these possibilities have like equal probability. So it doesn't like work because like when when you're here, you have like two choices, right? But hold on. Oh wait, no. It's like, say you stop when you reach. Okay, so say you stop when you reach like either of these 2 points here. So not every like possibility is going to have like an equal probability, because like say here, the only thing you can do is like go up, and but like on other spots you have like two choices, and yeah, so okay, that might have been actually not a good example, but yeah, so that's something to keep in mind. So Aaron's flipping 10 fair coins in a row. What's the probability of him flipping at least 5 heads and at least 3 tails? So our first thing here is we have to do some algebra to like actually understand these conditions. So I say there's like h heads, then we have like 10 minus h tails. So if like 10 minus h is like at least 3 and h is at least 5. This one's equivalent to h is less than or equal to 7. Okay, and so if he flips n heads, then there's like 2 minus, oh, so there's like 10, choose n ways to choose which of the coins have like heads, and there's like 10 to the power of 10 like total possibilities. Yeah, and our answer here is like this. And you just have to compute it out. It's not very hard. Okay, now here's our second example. 4 positive numbers less than 10 are chosen randomly. What's the probability that their sum is odd? And so again, we first have to like analyze the situation here to like figure out what we should do. So what different sums of odds and evens gives odds? So here's our like 2 cases. So if we have like 3 odds and 1 even, we have, okay, and there's like this many odd numbers. There's 5 odd numbers and there's like 4 even numbers here. So we have this. Oh wait, we're not doing that yet, but we're actually okay, yeah, so there's 4 choose 3 ways to choose which of the 4 numbers are odd, because like, so we have like these 4 numbers here, and we have to choose which one of these are odd. There's 3 odd, so there's 4 choose 3 ways to choose which ones are odd. And then here's what I was talking about before. We have to actually like determine the values of the odds and evens. Notice that the like, and it, oh, okay, I kind of like skipped this, but we don't need to like focus on the actual value. We focus on the parity, and we're going to be assigning the actual values at the end. So yeah, okay, and so how many ways can we determine the value of the evens and odds? Okay, so I said it before, where we have like 5 odds and 4 evens, and we do same thing for the other case. It's just the same process. Here's the actual answer, I believe. It's Yeah, I believe this is the answer here. Okay. Okay, and here's an exercise. I'll give you guys like a couple of minutes. Actually, this is like an Amy number 5, so it's like decently hard. Uh, for I wouldn't expect you guys to like actually solve it for right now, but because this is like an AMC 8 level class, but you should like think about it and try to see what you get. Okay, so I hope you guys had enough time. This is kind of a tricky question. So so our first step is we're framing the we have to like frame the problem in a way that like each possibility has like a equal probability. So we're or well like this makes it easier for us to like understand. So basically we're choosing 6 socks here from the drawer and then arranging them randomly, and that's like 10 choose 6 times 6 factorial, or like 10 times 9 times 8 times 7 times 6 times 5. And so in our first 2 socks that we have here are Monday, second 2 are Tuesday, and the last 2 are Wednesday. So for the fifth and sixth sock, oh, okay, so we're going to be working backwards here. So on Wednesday, we have 6 times 5 ways to choose what socks we want. Or, wait. Oh, we have 5 choose 2 ways. because we have to oh, we have 5 pairs of socks, sorry. So we have like 5 pairs of socks, and so and these 2 socks have to like match. So we have 5 pairs. We choose what pair we want, and then we choose like how we want to like permute it, basically. And that's 5 times 2. For the third and fourth sock, we have 4 pairs of socks remaining. Oh, and so we're going backwards in time from Wednesday to Monday. And so we have okay, so we have choose 2 possibilities here, and then we subtract out the number of like pairs of socks we can still form, and we multiply by 2. And because we can like permute the 2 socks, the pair of 2 socks, because in our framing, the pairs, we can like swap around these pairs, and it's like different. In general, when you're like doing like these probability questions, it like doesn't matter what like framing is, like if you count these as indistinguishable or distinguishable, because it like cancels out in the end, like, and you get the same answer anyways. So okay, and now for your first and second sock, we have 2 pairs and 2 unpaired socks. And we do the same thing again. We have 6 choose 2 total rays, and then we subtract out 2 because that's the number of like pairs. And we just like compute all of this out here. Okay, now we're going on to casework. So casework is the strategy of splitting up a problem into several cases. When we split into cases, we impose extra conditions and restraints to make it easier to solve. And these cases are disjoint and don't overlap usually. But like sometimes we do want overlap because it's like really hard to not get any overlap when you're doing casework sometimes. And then we just like subtract out the intersection of the cases, and we use a technique called the principle of inclusion exclusion. And okay, so we'll talk about this in a future lecture, hopefully. And there's no further reading for this slide here. So here's an example of casework. We already did some casework problems before, so yeah, I should have like ordered these slides a bit differently, but you should kind of have an idea about what casework is, because we've already used it a couple of times. Okay, so, and I'll give you like a couple of seconds to read the question. Okay, and here's, okay, so I'm going to assume you've read it. It's kind of long. So first we simplify the problem by like forgetting the distinction between brothers and sisters here, and like we just call both of them by the same like letter. And at the end we just multiply by 2 to the power of 3 or 8 to assign which ones are brothers or sisters here. And now, so we can let the Okay, actually, here's the diagram here. So we have like two rows, and we like the first child in the first row be A. So A's here. So where can A sibling sit? A sibling can sit like here, or here, or here. So, okay. Now, so let the second child in the first row be B. And then if in this case, B can sit, like B sibling can sit here or here. Actually, I should use a different color here. And okay. So, wait, no, sorry. Yeah, so B sibling can sit here in this case. And on the last case, here, B's sibling can sit here or here. Okay. And now, so how many of these arrangements are valid? So, looking here, so we have this arrangement here, but look, this forces the last two children to be like adjacent, so that's a no-no here. This one's valid. This one's also valid, and this one is not valid. This one's, oh, wait, sorry. Okay, I guess I have to use. Okay. Yeah, so we have two valid cases here. Yeah, so we have two valid cases, and okay, and there's 3 times 2 ways to choose, and we have so 6, and we multiply by 8 to get 48. Wait, hold on. Okay. That should be correct. Yep, it's okay. Okay, and here's our second example for casework. So, our first step here is we need to think about what we should do casework on. So, what conditions would make solving this like super easy? So if our ront instead chose from 0 to 2017, 2017, then Laurent's doing the same thing as Chloe, and because they're doing the same thing, the probability that they're like that Laurent gets the same gets a higher number is like 1 for 2, right? And if Laurent instead chose from 2017 to 4034, then it's obvious like Laurent's any number Laurent chooses is going to be higher than Chloe's number, because the minimum is 2017 here and the maximum is 2017 here. And notice that because it's like they're choosing a real number, we don't have to like worry about the edge case like if they're both choosing 2017, because like that has a probability of 0, and we can just like ignore it. Okay, and our answer is like this here. So it's going to be 3/4 in the end. And here's our exercise here. Wait, let me see if there's... Oh yeah, there's another exercise after this. Okay, I'll give you guys like a few minutes. You like, solve it by yourselves. Okay, so hopefully you had enough time to get like some progress on here. So here's our second exercise. This one's like kind of an essay, but it's actually pretty simple once you like understand what's happening here. Okay, so for the first exercise, so our casework is on the color combination that they both get. So, shoot, okay. So if both of them get R, or like red, so there's 10 choose 2 times 8 choose 2 ways, because there's 10 reds and you choose 2 of them, and after that there's 2 reds and you choose 2 of them again, and you just put them over the total number of possibilities. If both of them get BR, there's 10 B's here. There's 10 reds still. Then there's 9 B's and there's 9 reds. And so by symmetry, BB has the same probability as RR, and we sum them up because there's no overlap, obviously, because the cases are totally disjoint. And okay, and our second example here. So we do casework on a number of substitutions here. And so for 0 substitutions is one way. For 11 substitutions, so for one substitution, we have 11 ways to choose which player goes out. So we have 11 ways to choose which player goes out, and we have 11 ways to choose which players go in as a substitute. Okay, and so, and we do the same process here. There's 11 ways for like which player can go out. There's 11 ways for which player can go in. 11 ways for which player can go out again, including the substitute. And then we have like 10 substitute remaining, so we have 10 ways to choose which substitute we can go in. And yeah, so oh, and the point of this manipulation here is so we can, because we're finding this the remainder when it's divided by 1000, so this is kind of just like a convenient way to like cancel stuff out here, because like see, this is the same thing as here, and we just like do all of this here and we get an actually pretty nice answer here, because like these things cancel out. This is like 0 mod 1000. Okay, and see, end of, okay, that's the end of the slides. But we still have a couple of minutes left, so I'm going to go over a problem set for the last minutes of this lecture. So hold on for a few seconds. The problem set that I'm going to go for like because we're ending at about like 10:30ish, so we'll be going over this in the meantime. So wait, let me see if I can have two screens here. Okay. Is it too blurry for you guys? Can you still like read the problem set, or do you want to like for actually I can zoom in, I guess, kind of. Okay. So for number 1, the 2020 Summer AMC team needs to split up 3 unique jobs among its 8 members. If each member can do as many jobs as they please, how many ways are there to assign the jobs? So we have 3 jobs here, and for each job we have 8 ways to like choose which one. Ways to choose a team member, and there's 8 jobs, so we have 8 to the power of 3 equals 512. Okay, so for number 2, there's 52 postal abbreviations for the 50 states of America, DC, and Puerto Rico. if we choose a two-letter word as at random, what's the probability that we choose one of the 52 postal abbreviations? So there's 26 26 times 26 like random words, and we have like 52 postal abbreviations. So what we get is 1 over 13. How many ways can you arrange the letters in target? So we have, so a naive thing to do is just like there's 6 letters, so we have 6 factorial, but we notice that we have like 2 t's here, and so we have to divide by 2 factorial because we can permute these 2 t's 2 factorial ways, but like they're actually just the same like thing. So we have 360 here. Okay, so how many distinguishable arrangements of 1 brown, 1 purple, 2 green, and 3 yellow towers in a row from left and how many are there from left and right? Okay, so this is like the same idea as the last problem. So we have, so like if all of them are distinguishable, then we have like 7 factorial ways, but we have to divide by 3 factorial for like the yellow tiles because there's 3 yellows, and we can permute these 3 factorial times, but like they're all the same. 2 factorial for the green, and the rest of them are okay because they're only like technically there's like only one way to like permute them, so we can just like leave that out. And we just do some arithmetic here to get 420. If I wrote 5 standard 6-sided dice and multiply the number on each dice, what's the probability that the result's a composite number? So if you remember, the definition of a composite number is it can be written as the product of 2 numbers that are greater than 1. So at least one of, so at most one of the dice is greater than 1, and this dice that's greater than 1 has to be a prime. Okay, so we do casework here. So case, all of them are 1. So there's 1 over 6 to the power 5 here. And the second case is we have like 4 ones and 1 prime. So the prime can be 2, 3, 5. Oh, we're doing complementary counting. So this is complementary counting here. We're finding the probability is it is a prime, and then we're just subtracting it off. Or well, not. So probability that it's not a prime. There's actually a number that's not a prime or a composite number. 1. One's not composite or a prime, so I should say it's non-prime instead of, or well, non-composite instead of just like prime. Okay, so for this case, we have 5 choose 4 ways to like choose which of the dice is 1. And then we have like 3 ways to choose which prime it is, and we put that over 6 to the power 5. This is, wait, okay, yeah. If we sum them up, then we get 16 over power 6 over power 5. And we subtract from 1. And we just, yeah, so, and you just compute that out. Now we're on 6. How many positive integers less than 1000 have only even digits? Only have even digits, so so we can write any such numbers a, b, c, and for like this is the decimal representation. So note that a can be 0, b can be 0, and like yeah, so we allow leading zeros here. And so there's 5 primes include 5 even numbers including 0. So we have 5 choose 3 ways here. 5 to the power 3 ways here. So, and we subtract out the, like, when we have 0, 0, 0. Because that's not a positive integer, so we have 124. Okay, so now we're on 7. Okay, actually I should, sorry. Okay, I'll give you guys actually some time to solve 7. Because I realized I was kind of just like rushing out the other problems here. Okay. So okay, so we have two reds, two. Okay, I'm assuming you guys have like mostly solved it. So we have two reds, three blues, and four greens. Okay, so now we're doing casework on which one of them gets left out here at or yeah. So we're doing casework on which one gets left out. If a red gets left out, then we have one red, three blue, four greens. Is 8 factorial divided by 3 factorial divided by 4 factorial, which it, or yeah, 5 times 6 times 7 times 8 divided by 6, and that's 280. If we leave out a blue, we have two reds, two blues, and four greens. And that's 8 factorial divided by 2 factorial divided by 2 factorial divided by 4 factorial. And yeah, okay. Yeah, and this is just computation here for 20. And if we leave out a green, we have two reds, two blues, three blues, three greens. 8 factorial divided by 2 factorial divided by 3 factorial divided by 3 factorial, which is yeah, 560. And then we just add 280 plus 420 plus 560 to get to yeah 1260. Okay, also so that's the end of the lecture today. Do you have any questions on the prompts that I just ran over? If not, I'll be ending the meeting right now. Thanks for coming, and I'll upload the recording sometime later today. Okay, bye everyone. Have a good day. Keep warm.